Hello students, welcome to EPG Pathshala. I am Dr. Renu Tyagi from Sardar Patel Institute, Ahmedabad. Today we will learn about the module Physiological Adaptation to Heat and the Cold under the paper Physiology and Sports Anthropology. Now what are the learning objectives in this module? This module will focus on the physiological conditions and their responses to the thermal stress. It will emphasize on the exercise performance during heat and the cold stress. It will also highlight the physiological changes during the heat and the cold acclimatization. Humans have an immense capacity not only to adapt anatomically, biochemically and physiologically to a broad range of environmental stresses, but they also have the technological capacity to modify the local environment to support the life. These characteristics have been critical to the survival and advancement of the human species. The human encounter thermal, including the heat and the cold stresses from climatic conditions, insulation worn and the body heat production. Alteration in the body temperature, that is skin, muscles, etc. above and below the normal level can degrade the exercise performance and it may cause the thermal injury. Human regulates the core temperature within a normal range of 35 degrees Celsius to 41 degrees Celsius through two parallel processes, that is physiological and behavioral temperature regulation. The physiological temperature regulation operates through the responses that are independent of the conscious voluntary behavior, and it includes the control of the rate of metabolic heat production, body heat distribution via the blood flow from the core to the skin and by the sweating. The behavioral temperature regulation operates through conscious behavior and includes the actions such as modifying the activities level, changing the clothes and seeking the shelter. For humans, the physiological thermoregulation is most important during the heat stress and the behavioral regulation is most important during the cold stress. Humans demonstrate adaptation to repeated exposure to either heat or cold stress. In general, these adaptations act to defend the body temperature, reduce the physiological strain and improves the comfort work capabilities and reduce the susceptibility to thermal injuries. Acclimatization develops from challenges in the natural environment, and acclimatization develops from the exposed or the experimental exposure to the artificial conditions. Both elicit the similar adaptations. However, acclimatization can affect the adaptation to stimuli besides the thermal strain, such as diet and activity level. Here the focus is on human adaptation to the hot and the cold environment and the integrated physiological responses that accompany such adaptation. Now let's see the physiological adaptation to the heat stress. Humans have remarkable ability to adapt to the heat stress and give adequate water and protection from the sun. A healthy acclimatized person can tolerate extended exposure to virtually any natural weather related heat stress. Heat stress results from the interaction of environmental condition, that is temperature, humidity or sun, physical work rate, that is body heat production, and wearing of heavy clothing or equipments that impede the heat loss. Environmental heat stress and exercise interact synergistically to increase the strain on physiological system. This strain is manifested by high skin and core temperature, excessive cardiovascular strain, and reduced performance. Heat acclimation results in biological adaptation that reduce these negative effects of heat stress. One becomes acclimated to the heat through repeated exposure that are sufficiently stressful to elevate both core and the skin temperature and provoke profuse sweating. These biological adaptations occur from integrated change in thermoregulatory control, fluid balance, and cardiovascular responses. Let's understand the biophysics of the heat exchange and the balance. A muscular contraction produces metabolic heat that is transferred from the active muscles to blood and to the body core. Because skeletal muscles contraction is about 20% efficient, about 80% of the expended energy is released as heat that must be dissipated from the body to avoid the heat storage and increased body temperature. Physiological adjustments redirect blood flow from the body core to the periphery, thereby facilitating the heat transfer from within the body to the skin, where it can be dissipated into the environment. Heat exchange between the skin and the environment is governed by biophysical mechanism dictated by the surrounding air or water temperature, air humidity, air or water motion, solar, sky and the ground radiation, and clothing. Now let's have a look at this picture which shows us the avenues of the energy exchange for an athlete performing exercise in the air. The biophysical avenues of this heat exchange are conduction, convection, radiation, and evaporation, as it is clearly visible from this picture. Let's understand what is conduction. Conduction is the transfer of heat between two solid objects in direct contact, and convection is the exchange of heat between a surface and a moving fluid, including air or water. Heat exchange by conduction or convection occurs as long as there is a temperature gradient between the body surface and contacting objects or surrounding fluid. When a person is standing, walking or running and wearing shoes, heat exchange is by the conduction will be minimum because the thermal gradient between the body and contacted solids are usually small, as is the surface area for exchange. Now let's see what convection is. The convective heat exchange occurs when the surrounding fluid is moving, for example wind and the water circulation, relative to the body surface. In air environments, convective heat transfer can be significantly increased by wind if clothing does not create a barrier, and for the swimmer, convective heat loss can be very large even when the difference between the body surface and surrounding fluid temperature is small, because water has a much greater heat capacity than air. Heat loss by convection to air or water occurs when the air or water temperature is below body temperature, or conversely, heat gain by convection from air or water occur when the temperature exceeds that of the body. Let's see the radiation mechanism. The heat loss by radiation occurs when surrounding sun, sky, ground or other large natural or man-made objects have lower surface temperature than the body. And the heat gained by radiation occurs when surrounding objects have higher surface temperature than the body surface temperature. Radiative heat exchange is independent of an air temperature or motion. Accordingly, temperature combination of the sky, ground and surrounding objects may result in body heat gain due to radiation, even though the air temperature is below that of the body. For example, on a very sunny day, a mountaineer or a snowy surface may gain a significant amount of heat despite the low air temperature. And the heat loss from exposed skin is greater under a clear night sky than in daylight due to the radiative heat loss, even when the ambient air temperature are the same. Let's see evaporation. The evaporative heat loss occurs with the phase change when liquid turns to water vapor. In humans, evaporative heat loss is associated with breathing and perspiration. When water that is secreted into the skin via sweat glands or is rained or splashed onto the skin evaporates, or water from respiratory passages evaporates, the kinetic energy of the motion of the water molecule, that is the latent heat of the evaporation, will eliminate heat from the body. Evaporative cooling accounts for almost all heat loss during exercise at ambient temperature equal to or above the skin temperature, as studied by Farrell et al. In 2012. Let's see the physiological thermoregulation in human body. Humans regulate core temperature through two collaborative processes of temperature regulation, that is behavioral and physiological. Behavioral temperature regulation operates through the conscious alteration in behavior that can influence the heat storage, such as modifying activity level, changing clothes, and seeking shade or the shelter. Whereas the physiological temperature regulation operate through the responses that are independent of conscious voluntary behavior, such as controlling the rate of metabolic heat production like shivering, body heat distribution via the blood from the core to the skin, that is cutaneous vasodilation and constriction, and by the sweating. People often choose to ignore effective behavioral thermoregulation strategies because of their motivation to win or complete a task. Now let's have a look at this picture, which shows us the thermoregulatory response to the acute exercise heat stress and heat acclimation. As a result of excessive heat stress and heat acclimation, the thermal comfort and effector signal for the behavior goes to cerebral cortex, which results in the effector signal for the sweating and vasodilation to the sweat gland and the skin arteriole. It also sends an effector signals for the vasoconstriction in the skin arteriole and the superficial veins. And it shows an effector signal for the heat production in the skeletal muscles. Let's see how anterior hypothalamus center controls the heat balance. This center controls the heat dissipation events. If the center is stimulated, the blood vessels of the skin are dilated, thus resulting in a greater flow of blood to the surface. Also, the impulses are transmitted to the sweat glands, increasing perspiration, and to the respiratory center, causing panting. All these physiological responses act to increase the rate of heat loss from the body and thereby prevent overheating of the body. Let's see how does posterior hypothalamus center works. The posterior hypothalamus center calls on heat conservation events and thereby prevents chilling of the body. If the center is stimulated, the blood vessels of the skin are constricted, thus reducing the blood flow to the surface. Besides, it is well known that the surface hairs on the body are also stimulated to become erect, and thus they come into play to reinforce the insulating layer of the air surrounding the skin. At the same time, shivering is brought about through the same mechanism. Now let's see the role of adrenal, medulla and thyroid endocrine gland. The adrenal medulla and the thyroid endocrine gland also takes part in the regulation of heat production or heat loss. When the adrenal medulla is stimulated, large amount of epinephrine and non-epinephrine hormones are released into the blood. These two hormones have the ability to increase the basal metabolic rate and thereby increase the heat production. When the thyroid gland is stimulated, large quantities of the hormone called thyroid is released into the blood. The action of this hormone is similar to that of the non-epinephrine. However, thyroid hormone continues to be active for as long as 4 to 8 weeks after its release into the blood. Non-epinephrine, on the other hand, remains active only for few minutes. Now let's have a look at the core temperature. The measurement of the body core temperature is fundamental to the study of human temperature regulation. Core temperature is measured either to estimate the core temperature input to thermoregulatory control or to estimate average internal temperature to compute changes in heat storage in the core. Brain or hypothalamic temperature during exercise is generally accepted to be similar to the blood temperature. However, recent evidences suggest that it could be slightly higher. There is no one true core temperature because temperature varies among sites deep inside the body. The temperature within a given deep body region depends on the local metabolic rate of the surrounding tissues. It depends on the source and the magnitude of the local blood flow, and it also depends on the temperature gradient between contiguous body regions. Considerable temperature gradient exists between and within the orifices, body cavities, and the blood vessels. For resting humans, internal organs and viscera within the body core produce about 70% of the metabolic heat. During dynamic exercise, however, skeletal muscles produce up to about 90% of the metabolic heat. Because metabolic heat source changes during exercise as compared with the rest, the temperature change measured in one body region during exercise may be disproportionate to those measured in other body regions. During rest in a comfortable environment, skeletal muscles temperature is lower than the core temperature. But during the exercise, the temperature within the active skeletal muscles often exceeds core temperature. Blood that is perfusing active skeletal muscle is warmed and the blood then carries that heat to other body regions, resulting in an elevation in core temperature. Core temperature during exercise is often measured at the esophagus, rectum, mouth, tympanum or auditory meatus. In brief, most physiologists consider esophageal temperature to be the most accurate and reliable non-invasive index of core temperature for humans, followed in preference by the rectal temperature and gastrointestinal tract temperature measured with the use of ingestible temperature sensor pills. Sensor pills are ideally suited for ambulatory monitoring outside of laboratories, but their values are variable and dependent on location within the gastrointestinal tract. Rectal and gastrointestinal tract temperature are often slightly higher and slower to respond than esophageal temperature. Tympanic and auditory meatus temperature are widely used to reflect core temperature but are less reliable indices of core temperature than the other measures. This scheme presumes that thermal receptors in the core and skin send information about their temperature to some central integrator. Any deviation between the controlled variable body temperature and a reference variable that is a set point temperature constitutes a load error that generates an efferent signal to control sweating, vasodilation, vasoconstriction, and shivering. Exercise and fever both increase the core temperature of human body, but the acute exercise does not alter the set point, whereas fever does. The metabolic heat production increases immediately with the initiation of exercise, causing the heat storage and thus creates a difference between the set point temperature and the elevated core temperature. The set point temperature is unchanged and therefore heat dissipating responses are elicited to the core temperature. This increases until the heat loss response is sufficient to match the heat productions are achieved and a new thermal balance is established. When exercise stops, the heat loss exceeds the heat production and thus the core temperature fall back towards the set point. This diminishes the signal or the load error, eliciting the heat dissipation responses and they decline to the baseline level as the thermal balance conditions prevailing before exercise are re-established. Therefore, the primary event elevating the core temperature during exercise is increased metabolic heat production. In fever, the primary event is an elevation of the set point temperature. Heat dissipating responses are inhibited and or the heat production is stimulated until the core temperature increases enough to re-establish the thermal balance of a new set point temperature, at which the heat production and heat loss are near their values before the fever. The inhibition of the heat dissipation and stimulation of the heat productions act independently as a result of the person's thermal state and the environmental temperature. When the fever abates, that is the set point returns to the normal, the heat dissipating responses are increased and or the heat production is reduced until normal thermal balance is re-established. If an individual exercise while having a fever, the exercise hyperthermia will be imposed above the fever temperature. Now let's see what is acute heat stress. The temperature regulation during exercise in hot climate involve vasodilation and sweating as a function of anterior hypothalamus of the brain. Vasodilation increases expansion of a blood vessel, increases the skin blood flow and thus enhances the transfer of metabolic heat from the deep core to the skin surface. Secretion of the sweat, on the other hand, provides water for evaporative cooling. A general increase in blood flow from the deep core to the skin and limbs by the circulatory system allows for a greater amount of the heat to be lost by conduction, convection, radiation and evaporation. As the cooled blood returns to the deep core area, it once again picks up the heat and transport it to skin, where it is dissipated in the manner. During sweating, when the environmental temperature rises above the skin temperature, that is more than 34 degrees Celsius, the circulatory adjustments are not sufficient for the heat dissipation by convection and radiation mechanism because of the reduced gradient or the negative gradient between the skin and the environment. Thus, the only means for the heat loss at a temperature above the skin temperature is by evaporative sweating. At the same time, however, if the rate of metabolism is increased by exercise, the sweating must be called upon at a lower temperature. The reduced thermal and the vapor pressure gradient in a hot and humid climate put a strain on the cardiovascular system and evaporative sweating mechanism. In weather that is hot and humid, it is common knowledge that the heart has to work much harder than the normal Because the amount of the blood flowing through the skin is generally increased due to the vasodilation of the skin and blood vessels, and it is highly saturated with the oxygen. As a result, less oxygen is available to the working muscles, and hence the lactic acids start accumulating in the blood at a much lower intensity of work. Therefore, humidity poses additional heat dissipation problem. Because of the added strain to the circulatory system to provide sufficient blood to the working muscles and to the skin for heat dissipation, it is quite obvious that exercise in environmental surroundings of high temperature and high relative humidity can place a severe strain upon the cardiovascular system. The ability of an individual to perform the prolonged moderate work in a hot and a dry climate is not limited by the evaporative process as in the hot and the humid climate. In hot and the dry climate, the ambient air can absorb larger amount of moisture before becoming saturated. While working in this kind of climate, however, heat must still be taken from the core to the skin for the heat dissipation in order to maintain a normal body temperature. This requires adjustment on the circulatory system from its normal state. Since the volume of the oxygenated blood flowing through the skin is normally increased as a result of vasodilation in the skin blood vessels, the heart has to work much harder. Again, because less oxygen is readily accessible to the working muscles under these conditions, the lactic acid starts to accumulate in the blood at a somewhat lower intensity of work. As a result of the increased strain on the circulatory system to furnish the sufficient blood to the active muscles and to the skin for the heat dissipation, it can be seen that work in a climate close in or above skin temperature can place severe strain on the cardiovascular system even when the external air is relatively dry. Let's see the effect of extreme heat. The major one is the dehydration. People working in intense heat can lose about 2 or more liters of body fluid per hour for periods of 5 hours or longer. The loss of body fluid is the most serious problem of sweating, and it can lead to the dehydration. Dehydration is common in workers in the hot climate. It is due to the excessive amount of water being lost in the sweat without an adequate replacement. A drop in the body fluid during prolonged exercise is not only accompanied by increase in body temperature, but also a reduction in cardiac output, stroke volume, blood volume, velocity of blood flow, and a fall in blood pressure. And all these changes will adversely affect their performance unless body fluids are replenished to facilitate the sweating mechanism and to help the body temperature at a lower level. The loss of body fluid during excessive sweating not only results to dehydration but also to the salt imbalance within the body, and if not replenished by either additional salt in the daily diet or perhaps a daily salt tablet, it may lead to fatigue, nausea and the heat cramps. Let's see the cardiovascular effects of the extreme heat. During exercise, in the heat, the primary cardiovascular challenge is to increase the cardiac output sufficiently to support both high skin blood flow for heat dissipation and high muscle blood flow for metabolism. Exercise heat stress increase blood flow to the skin and usually sustains muscles blood flow relative to temperate conditions. However, reduced muscles blood flow has been observed during maximal exercise with heat stress. The cardiac output elevates during mild and perhaps moderate exercise in the heat compared with the similar exercise in temperate conditions. During high and maximal intensity exercise in the heat, cardiac output can be below levels observed during similar exercise in temperate conditions. The lower cardiac output during maximal exercise results largely from an inability of the heart rate to compensate for reductions in stroke volume associated with high skin blood flow and peripheral pooling of blood. Coronary blood flow is believed to be unaffected by excessive heat stress. However, as a result of increased sympathetic activity and thermal receptor stimulation, visceral blood flow is reduced by both exercise and heat stress. The visceral blood flow reductions are graded with the intensity of exercise, and the effects of exercise and heat seems to be additive. The mechanisms that are responsible for change in this splanchnic blood flow are probably quite complex. Reduced visceral blood flow allows a corresponding diversion of cardiac output to skin and exercising muscles and help support blood pressure. Also secondary to reduced visceral blood flow, a substantial volume of blood can be mobilized from the compliant splanchnic beds to help maintain cardiac filling during exercise heat stress. If these compensatory responses are insufficient, skin, muscle, and even brain blood flow may be compromised. Let's understand the heat acclimatization. Heat acclimatization induces biological adjustment that reduce the negative effects of heat stress. Heat acclimatization develops through repeated heat exposures that are sufficiently stressful to elevate both core and the skin temperature and provoke profuse sweating. The biologic adjustments are mediated by the integrated change in thermoregulatory control, fluid balance, and cardiovascular responses. In addition to these systemic adaptation, research has shown that cellular adaptation may also occur. The magnitude of the biological adaptation induced by heat acclimatization depends largely on the intensity, duration, frequency, and number of heat exposure. Exercising in the heat is the most effective method for developing heat acclimatization. However, even resting in the heat results in limited acclimatization. Usually about 7 to 10 days of heat exposure are needed to induce the heat acclimatization. An optimal heat acclimatization requires a minimum daily heat exposure of about 2 hours combined with the dynamic exercise that requires cardiovascular endurance rather than resistance training for development of muscular strength. Individuals should gradually increase the exercise intensity or duration each day of the heat acclimatization. During the initial exercise heat exposure, physiological strain is high as manifested by the elevated core temperature and the heart rate. The physiological strain induced by same exercise heat stress decreases each day of the acclimatization. Most of the improvement in heart rate, skin and core temperature and sweat rate are achieved through daily exercise in a hot climate during the first week of exposure. The heart rate reduction develops most rapidly in 4 to 5 days. After 7 days, the reduction in heart rate is virtually complete. The thermoregulatory benefits from heat acclimatization are generally thought to be complete after 10 to 14 days of exposure. However, it may take longer to achieve improvement in the physiological tolerance. Heat acclimatization is transient and gradually disappears if not maintained by continued repeated heat exposures. The benefits of heat acclimatization will be retained for about 1 week and then decay with about 75% loss by about 3 weeks once heat exposure ends. Let's have a look at this table which summarizes the action of heat acclimatization. This shows that there is a change in the thermal comfort which is improved, and there is a change or improvement in the exercise performance. The thermal comfort includes the reduction in core temperature, improved sweating, earlier onset, higher rate, redistribution, and improved resistance, improved skin blood flow, earlier onset, and higher rate of metabolic rate lowering. The exercise improvement include the improved cardiovascular stability, lowered heart rate, improved stroke volume, the blood pressure is better defended, myocardial compliance is improved, fluid balance is improved, thirst is improved, electrolyte loss is reduced, total water is increased, and plasma volume is increased with better defense mechanism. Let's see some of the physiological adaptation to the cold stress. The principal determinant of cold stress during outdoor event in cold weather are the air temperature and the wind speed. Most body heat loss during cold exposure occurs via conduction and convection mechanism. Therefore, when ambient temperature is colder than the body temperature, the thermal gradient favors the body heat loss, and wind exacerbate the heat loss by facilitating convection at the body. The physiological responses to cold include the acute cold exposure. The human exhibit peripheral vasoconstriction upon exposure to the cold. The resulting decrease in peripheral blood flow reduces convective heat transfer between the body's core and the shell, that is the skin, subcutaneous fat, and skeletal muscles, effectively increasing insulation by the body's shell. Because heat is lost from the exposed body surface faster than it is replaced, skin temperature declines. During whole body exposure to cold, the vasoconstrictor response extends beyond the fingers and spread throughout the entire body's peripheral shell. Vasoconstriction begins when skin temperature falls below about 35 degrees Celsius and become maximal when skin temperature is about 31 degrees Celsius. Therefore, the vasoconstrictor response to cold exposure help retard heat loss and defends the core temperature, but at the expense of a decline in the temperature of peripheral tissues. The reductions in the vasoconstriction induced blood flow and skin temperature probably contribute to the causation of peripheral cold injuries. Cold-induced vasoconstriction has pronounced effect in the hands and the fingers, making them particularly susceptible to cold injury and loss of manual dexterity. In these areas, another vasomotor response, cold-induced vasodilation (CIVD), modulates the effects of vasoconstriction. Periodic fluctuation of skin temperature follows the initial decline during cold exposure, resulting from transient increase in blood flow to the cooled finger. A similar CIVD in the forearm appears to reflect vasodilation of muscles as well as cutaneous vasculature. Although this was originally thought to just be a local cooling effect, evidence suggests that a CNS mechanism mediates, and the response is modulated by hypothermia. Cold exposure also elicits increased metabolic heat production in humans, which can help offset heat loss. In humans, most cold-induced thermogenesis is attributable to skeletal muscle contractile activity. Humans initiate this thermogenesis by voluntarily modifying their behavior or by the shivering. Shivering consists of involuntary repeated rhythmic muscle contraction during which most of the metabolic energy expended is liberated as heat and little external work is performed. It may start immediately or after several minutes of the cold exposure and usually begins to torso muscles and then spread to the limbs. Let's have an idea about the pattern of human cold acclimatization. The people who are exposed to the cold weather can acclimatize, but the specific physiological adjustments are modest and they depend on the severity of the exposure. The cold acclimatization in persons who are repeatedly or chronically exposed to the cold is manifested in the three patterns of thermoregulatory adjustment. They are habituation, metabolic acclimatization, and insulative acclimatization. The most commonly observed acclimatization pattern is habituation. With habituation, the physiological responses to cold become less pronounced than before acclimatization. The blunting of both shivering and cold induced vasoconstrictions are the hallmark of habituation. Sometimes, not always, the cold habituated people with blunted shivering and vasoconstrictor responses to cold also exhibit a more pronounced core temperature change during the cold exposure than the non-acclimatized people, a pattern called the hypothermic habituation. Taken together, findings from different cold acclimatization studies suggest that the distinction between studies that observed the hypothermic habituation and those in which the habituation of shivering and vasoconstriction occurred without effect on the core temperature response to cold probably reflect the differences in experimental protocols rather than physiological mechanisms. Now, this table summarizes the influence of chronic or repeated cold stress. As we can see, the cold habituation imposed the blunted shivering, blunted cutaneous vasoconstriction. The metabolic acclimatization includes enhanced cutaneous vasoconstrictions, improved muscle blood flow, which redistributes the body heat towards the body shell. The insulative acclimatization include enhanced shivering thermogenesis and enhanced non-shivering thermogenesis. Let's have a look at the individual factors that modify the response to the cold. The major anthropometric characteristics include that the person with a larger ratio of surface area to mass have greater decline in body temperature during cold exposure than those with a smaller ratio. Subcutaneous fat provides a significant insulation against heat loss in the cold. Therefore, fat persons have smaller body temperature change and they shiver less during the cold exposure than the lean people. Women have a greater surface area but smaller total body mass than men. Therefore, even though insulation is equivalent, total heat loss during resting cold exposure will be greater in women because they have a larger surface area for convective heat flux. The reduced vasoconstriction and heat conservation results among the older people with less tolerance to the cold than the younger people. The aerobic fitness and training is also influenced. The exercise training and aerobic fitness appears to have only minor influences on thermoregulatory response to the cold. Heat production during high intensity exercise can be sufficient to prevent a fall in deep body temperature without the need for heavy clothing even when air temperature is extremely low. Let's have a look at the influence on the exercise in the cold. Because of the cold temperature, the oxygen uptake is higher during the steady state submaximal exercise in cold temperature, with an increased oxygen uptake representing the added oxygen requirement for metabolism in the shivering muscles. There is an increase in the cardiac output in response to the shivering. And for a given cardiac output, heart rate lowers and stroke volume increases. The muscle energy metabolism also changes. There is an increased energy requirement of shivering, which result in the increased glycogen breakdown during the exercise, and that shivering preferentially metabolizes the muscle glycogen as an energy source. During exposure to the cold, the thermogenic response during the exercise ensure that increased metabolic heat production will usually match exercise-related facilitation of the heat loss, and exercise performance will not be affected by the inability to maintain thermal balance. Now let's summarize the module. The body temperature is regulated by the two distinct control systems. The one is behavioral system and another is the physiological system. The behavioral thermoregulation involves the conscious or willed use of whatever means are available to minimize the thermal discomfort. On the other hand, the physiological thermoregulation employs the unconscious responses that are controlled by the autonomic nervous system in proportion to the core and the skin temperature. The physiologic responses that modify the body heat loss are vasodilation and sweating, and those that modify the heat conservation are the vasoconstriction and shivering. Thermoregulatory responses are affected by an interaction among exercise duration, intensity, and the mode, as well as the environmental and individual characteristics. Climatic heat stress and exercise interact synergistically and may push the physiological systems to their limits. The heat stress reduces an athlete's ability to exercise. Physiologic mechanisms that contribute to this reduced performance include the cardiovascular, central nervous systems, and metabolic perturbations. The heat acclimatization provide many physiological adaptation to allow the sustained exercise and protection from the heat injury. Athletes routinely have high sweating rates during the exercise heat stress that can lead to the dehydration and adversely influence the exercise performance. In the cold, the heat balance and requirements for shivering depends on the severity of the climatic cold stress, effectiveness of the vasoconstrictions, and intensity and mode of the exercise. The cold-induced vasoconstriction decreases the blood flow to the peripheral tissues, which allows them to cool and make them susceptible to the cold injury. The cooling of the peripheral tissues can degrade the finger dexterity and impairs the skeletal muscles contractions functions, whereas a reduced core temperature can degrade the body's ability to achieve the maximal metabolic rates and with the maximal endurance performance. Body composition is the most important physiological determinant of the thermoregulatory tolerance to the cold exposure. The clothing requirement for the warmth and the comfort is much higher during the rest and light activity than during the strenuous activity, and over insulations can cause the heat stress that lead to sweating, wet clothing, and dehydration. Each of these factors can have the undesirable influence on the athlete's performance and susceptibility to the cold injury. Thank you.